Section: Introduction. In this section, we will first summarize the concept of hypernetworks and standard multi-head dot product attention before explaining how attention can be represented as a hypernetwork. We will then introduce hypernetwork linear attention, HYLA, as a straightforward modification of linear attention that enhances the hypernetwork mechanism within attention. For notation, we will use bold lowercase letters for vectors, e.g., Z, bold uppercase letters for matrices, e.g., A, and bold, italic uppercase letters for learnable parameter matrices, e.g., WV. Regarding multi-head attention, a hypernetwork is a neural network H, Z, theta, controlled by theta that takes a latent code Z as input and produces parameters W that define a value network F, X, W, which processes the inputs. The latent code Z is usually low-dimensional and specifies the computation carried out by the value network. Multi-head attention can be seen as a linear hypernetwork generating the weights for a linear value network. This differs from the idea that linear attention acts as a fast weight programmer where the fast weights of a value network are formed as a sum of outer products over the key indices rather than the head indices. Self-attention maps a sequence of inputs X in RT times D to a sequence of outputs Y in RT times D. For each attention head H in 1, H, the inputs are projected into keys KH equals XW key and queries QH equals XW query using head-specific projection matrices wiki, query. The attention matrix is then obtained, whereas stacks the head-specific unnormalized attention matrices into a three-dimensional array and applies a normalization operation sigma, dot operator. In the case of linear attention, sigma, dot operator, equals ID, dot operator, is simply the identity function, while for softmax attention, sigma, dot operator, equals softmax, dot operator, applies the softmax operation independently across the key indices for each head and query index. Multi-head attention, MHA, can be equivalently expressed as a hypernetwork with a key query-specific latent code, where the attention scores over the multiple heads form a latent code. This latent code configures the computation implemented in the linear value network. Our discovery suggests that multi-head attention can execute specialized, reusable operations through the hypernetwork's latent code. Importantly, hypernetworks support compositional generalization, which may explain similar capabilities observed in transformers. Inside multi-head attention, the same hypernetwork is utilized for every key query index, promoting the reuse of latent codes and their associated operations implemented through the value network. Section Summary. In this section, we introduce hypernetwork linear attention, HYLA, as a modification of linear attention that enhances the expressiveness of the hypernetwork mechanism within attention. Multi-head attention can be viewed as a linear hypernetwork that generates weights for a linear value network, enabling specialized and reusable operations through the latent code of the hypernetwork. Our findings suggest that multi-head attention can implement configurable computations through a shared hypernetwork, supporting compositional generalization and potentially explaining the transformative capabilities observed in transformers. Section: Hypernetwork linear attention, HYLA. In this section, we explore how we can enhance the multi-head attention mechanism by introducing a modification called hypernetwork linear attention, HYLA. By making the value network nonlinear and normalizing the latent code along the head index, we aim to improve the expressivity of the learned subfunctions. This modification involves using a single hidden layer value network with nonlinearity and normalizing the attention scores for each key and query index independently across the head indices. The HYLA layer serves as a simple replacement for standard attention, where the value network is more expressive, enabling the network to perform more complex operations for a given latent code. This enhancement is expected to strengthen the network's ability for compositional generalization. By adopting the hypernetwork perspective, we can consider different levels of granularity. For example, the hypernetwork could parameterize a query-specific value network, potentially facilitating the reuse of sequence-level operations. However, for the purpose of this paper, we focus on the key query level to delve into the inner workings of multi-head attention. We then delve into learning fuzzy logic functions in an in-context learning setting to study how well multi-head attention-based models can compositionally generalize. By defining fuzzy logic operators and tasks with compositional structures, we aim to analyze the model's ability to solve these tasks and understand the structure of their latent code. Our investigation shows that all models, including Hyla, can solve fuzzy logic tasks effectively when an adequate number of examples are provided in context. Hyla demonstrates better performance in compositional generalization compared to standard multi-head softmax attention and linear attention. The enhanced performance of Hyla is attributed to the more expressive value network, which aids in effectively representing the composed terms due to its nonlinear behavior. In summary, our findings suggest that the modifications introduced in Hyla, such as the nonlinear value network and normalization techniques, contribute significantly to the model's ability to generalize compositionally. Section Summary. In this section, we introduce Hypernetwork linear attention, Hyla, as a modification to linear attention by making the value network nonlinear and normalizing the latent code along the head index. Hyla enhances the expressivity of subfunctions learned by the layer and maintains linear time inference complexity without requiring communication across keys. By improving the value network's expressiveness, Hyla strengthens the ability for compositional generalization in multi-head attention-based models when solving fuzzy logic tasks. Section: Structured latent code. In this section, we examine the structure of the latent code in different models used to solve a task. We look at how attention scores influence the computation in the value network based on key query pairs. We hypothesize that these attention scores reflect the fuzzy logic function needed to predict the output of a query token accurately. To test this hypothesis, we gather attention scores for the final query token focusing on itself. This gives us a vector of size h for each layer and task. By visualizing these h-dimensional points using TSNE, we observe that the second and final layers of all models exhibit distinct clusters, which align with the target values of the functions for a given query. Interestingly, when we color the data points based on the fuzzy logic function of each task, we find that the clusters in the latent codes closely match these functions. We introduce a symbolic abstract reasoning task called SRAVEN, based on Raven progressive matrices, to study compositional abilities. Unlike previous machine learning datasets inspired by Raven progressive matrices, our task is symbolic, compositional, and addresses the challenge of searching through numerous hypotheses. This aspect, described as finding correspondences, has not been explicitly modeled in earlier benchmarks. The SRAVEN task involves predicting the contents of a final query panel based on a matrix of 8 context panels, each defined by a vector of integers. Rules are applied within each row to generate the panels, with a limited set of possible symbols. A sequence model predicts each dimension of the final query panel independently based on the context panels. The task's compositional structure tests the system's ability to generalize to unseen rule combinations by splitting them into train and test sets. This ensures that the agent encounters new task instances during evaluation that were not seen during training. Section Summary. In this section, we analyze the latent code structure of different models used to solve a task, focusing on attention scores and how they relate to the fuzzy logic functions needed for accurate predictions. By visualizing the attention scores using TSNE, we observe clear clusters in the final layer of all models, with these clusters closely corresponding to the underlying functions. We introduce a symbolic abstract reasoning task called SRAVEN based on Raven progressive matrices, aiming to study compositional abilities and the challenge of searching through numerous hypotheses to find solutions, a key aspect not explicitly addressed in previous benchmarks. Section: Finding correspondences. In this section, we simplified the task by using symbols instead of images of geometric shapes. This approach has the advantage of reducing the input space, making it easier to work with larger models and data in our experiments. However, it eliminates the step of learning from visual representations to discover the correct symbolic abstractions. We believe that the main challenge in the original Raven tasks lies in finding connections between rules and feature dimensions, rather than in visual representation learning. When tackling a task like the one shown in Figure B, a test subject may initially think that there is a rule governing the number and orientation of shapes. However, the correct solution may involve grouping the panels based on their orientations instead. To address the challenge of finding these connections in SRAVEN, we allow for permutations of the features, making it harder to find the right solution due to the increased number of possible hypotheses. Scaling the model size and data helps in generalizing compositionally. By training on more instances and increasing the model size, transformers can effectively solve 80% of the held-out problem instances with the right amount of data and model size. Introducing nonlinearity in HYLA seems to improve the performance, especially with fewer instances and smaller models. Analyzing the latent code of the models reveals a structured code that aligns with the task rules. Multiple heads in attention help in configuring compositional computations in the value network, aiding stability during training. Scaling pre-trained large language models enhances their ability to generalize compositionally on semantic parsing tasks. Various Raven-inspired tasks assess abstract reasoning abilities of neural networks by applying rules to feature dimensions. Our SRAVEN variant introduces the additional challenge of finding correspondences between rules and features, which sets it apart from other tasks based on simple geometrical shapes. Section Summary. In this section, we discuss the importance of finding correspondences in symbolic tasks like SRAVEN, where scaling models and data sizes can enhance compositional generalization. By allowing permutations of features, we make the task more challenging, yet manageable, with less than 0.5% of instances having multiple valid answers. Scaling experiments show that transformers can effectively solve 80% of problem instances when trained on a sufficient number of instances and with increased model complexity, highlighting the benefits of expressive value networks and structured latent codes in solving abstract reasoning tasks. Section Discussion. In this section, we have introduced a new way to break down multi-head attention, showing that it can be viewed as a hypernetwork that creates specific value networks for each key query pair. Our experiments confirm that the attention scores across different heads for each key query pair form a structured space, revealing reusable subfunctions in abstract reasoning tasks. Enhancing the hypernetwork mechanism in multi-head attention leads to better generalization on these tasks. We have explained that multi-head attention determines how detailed the hypernetwork parameterizes the value network. The value networks are tailored to each key query pair, and aggregation over keys is achieved through summation. Our analysis offers a fresh perspective on attention-based graph neural networks. Instead of viewing a non-causal single-layer transformer as a fully connected graph where each token is a node and aggregation is through attention, we propose a different interpretation. Here, the message function acts as a hypernetwork that encompasses the attention weights, while aggregation is done through summation. Given the importance of aggregation in graph neural networks, it is worth exploring if different pooling methods should be considered for multi-head attention. We have mainly focused on models trained from scratch to have precise control over the training data. However, there are intriguing behaviors in large-scale models pre-trained on various tasks. Investigating if these models exhibit a similarly structured latent code is a promising direction for future research. It is also valuable to explore if emphasizing the hypernetwork perspective is generally advantageous for transformer-based models. Although not the main focus here, we have conducted initial experiments on autoregressive language modeling with small-scale transformer models in the appendix. Our findings show that HYLA outperforms linear attention but lags behind softmax attention. The softmax fosters competition among key indices, introducing interactions between latent codes for shared query indices. Future studies will delve into the implications of this interaction on the latent code structure in scenarios where softmax brings significant benefits. Our work contributes foundational research that aims to clarify how the widely used multi-head attention layer functions. While we do not anticipate any immediate negative societal impacts, we believe that our study can enhance our comprehension of this extensively applied technology.